Hello, ladies and gentlemen. This is Mr. Briggs. I'm coming to you today from a strange woodland forest. I got lost. My parents said we were taking a walk, and I can't seem to find them now, and there seems to be this house made out of gingerbread and candy. I think there's an old lady inside. She seems really nice. I better keep walking. So here's how math works for today. Today we're doing filling and wrapping 2.2. 2.2 is called Saving Trees, and it takes place on page 20, A through D. You're going to need to do some reading on this page to kind of explain the problem, and your ACE problems are going to be 4 through 6, and 23 through 24, and then 28. And your learning target is that I can get the most volume for the least amount of surface area. Alright, ladies and gentlemen, let's get started. Okay, volume. Well, what is volume? We explained it before, but just to go over it again, volume is how much a shape can hold. It's answered using several different common volume measurements, such as cups, or gallons, or ounces, or pints, or liters. I really prefer liters. Why do I prefer liters? Well, because liters directly translate to cubic units. And cubic units are how we measure the volume of stuff. We use cubic inches, or cubic feet, or cubic centimeters. Now, here's a fun fact. If I have 1,000 cubic centimeters, right? 1,000 little centimeter cubes, that is exactly 1 liter. And guess how much that weighs? Exactly 1 kilogram. Guess how many cubic inches go into a gallon? 231. Really complicated. I don't like it. But moving on. We want to study today the relationship between surface area and volume. Now, we learned in our last lesson that surface area is what it takes to wrap an object. It is the outside surface of an object if we were to fold it flat. And volume is how much it can hold. Now, here is an example problem. I'm packaging 27 cubic centimeters worth of juice. Which box dimensions would use the least amount of paper? A box that is 3 by 3 by 3, 1 by 3 by 9, or 1 by 1 by 27. Now you might say to yourself, Mr. Briggs, well, if they all hold 27, they'll all have the same surface area. And you would be wrong, because we're going to set up a little table here. Now you'll need to set up about 3 of these for lesson 2.2. One for a box that holds 8 cubic centimeters, one that holds 27 cubic centimeters, and I believe one that holds 12 cubic centimeters. And here is how it works. For my first one, I have a dimension of a box that is 3 by 3 by 3. Well, what is 3 by 3 by 3? If I do 3 times 3 times 3, I get a volume of 27 cubic centimeters, right? And if I have a 1 by 3 by 9 box, well, 1 times 3 times 9 also gives me 27 cubic centimeters. And if I have a box that has 1 by 1 by 27, I also do 1 by 1 by 27, also gives me 27 cubic centimeters. Now, if you're a little confused on how to do these problems, you might find it easy to borrow a handful of the connecting cubes, or cubes that I have lying around, and you can, set them up, take out 27 of them, and see how many different boxes you can make. There is no shame in playing with little blocks. But now, here's what happens. If I do a surface area of 3 by 3 by 3, okay, this side is worth 9, that 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 side is worth 9, okay, because this side here is 3 wide and 3 tall. Each of its 6 sides are worth 9, so I'm going to have 54 square centimeters. I should label that better. 54 centimeters squared for a surface area. It's going to take that much paper to make the box. But now if I have my 1 by 3 by 9, well, this side right here is 1 by 3, which means it has an area of 3 cubic centimeters, or 3 square centimeters. This end has 3 square centimeters, because remember, this side matches, I just can't see it. This top is 1 by 9, so it has 9. I have another bottom here with 9 that I can't see. And this one here has a area of 27 because it's 3 by 9. And I have another side here that is also 27. And if I add those up, 9 plus 9 plus 3 plus 3 plus 27 plus 27, okay, those are the areas of all those faces. What do I get? I end up getting an area of 78 centimeters squared. That is really, really, really a lot more paper, right? 26 square centimeters more paper exactly. Well, what happens if I've got a box that is 1 by 1 by 27? This is a ridiculously long box. It's 27 centimeters long, and it is 1 by 1. Well, if I realize that this end here is 1 square centimeter, this end here is 1 square centimeter, and I just take 4 times 27 to get all 4 of those other sides, I end up getting an area that has 27, 27, 27, 27, plus 1, plus 1. And 27 times by 1 gives me an area of 110. So I end up getting 110 centimeters squared. More than twice the other box, my original box. So a much, much bigger waste of paper. So as you can see, there seems to be a way that we can get the most volume with the least amount of surface area. We can find a really efficient box. And you'll notice, as you complete the rest of 2.2, that there are certain shapes seem to use their surface area better. They seem to hold more for their shape. Okay? And that work takes place on page 20, A through D, the ACE problems 4 through 6, 23 through 24, and 28. Have fun!